Welcome back to another video. The F distribution is a right-skewed continuous probability distribution that is bounded at 0 and is asymmetrical with a longer tail on the right. It is defined by 2 degrees of freedom, one for the numerator, d1, and one for the denominator, d2. Although it has a very complicated PDF, it can be constructed by finding the ratio of 2 chi-squared distribution divided by their degrees of freedom. The degrees of freedom of these chi-squared distributions define the d1 and d2 parameters of the F distribution. F distribution arises frequently in statistics, particularly in the context of comparing variances of 2 normal populations. We previously introduced chi-squared statistics for defining a confidence interval on variance of a single population. Now, we can create 2 independent chi-squared statistics and use them to build a F statistic to compare the variances of 2 different populations. If x1 to xn is a random normal sample from our first population and y1 to ym is our second random normal sample from a different population, we can define 2 different chi-square distributions as n-1 times s squared of x divided by sigma square of x and m-1 times s squared of y divided by sigma square of y with degrees of freedom of n-1 and m-1, respectively. If we divide these chi-square statistics with their degrees of freedom and find the ratio of these divisions, we will have an F statistic with n-1 and m-1 degrees of freedom. Another interesting fact about F distributions is their reciprocal property. As we just discussed, the F statistic is the ratio of 2 scaled independent chi-squared random variables, each divided by their respective degrees of freedom. So if random variable f follows an F distribution with n and m degrees of freedom, 1 over f would follow an F distribution with m and n degrees of freedom. Now in terms of f values, the value f of alpha with m and n degree of freedom corresponds to the upper alpha percentile of the F distribution with m and n degrees of freedom. Similarly, f value of 1 minus alpha with n and m degrees of freedom corresponds to the lower 1 minus alpha percentile of the F distribution with n and m degrees of freedom. Intuitively, this property reflects the symmetry in the F distribution when considering the ratios of variances. It ensures consistency when degrees of freedom are swapped between the numerator and denominator, preserving the reciprocal relationship between the critical values. Here we want to study the variances of 2 normal distributions. As we are hypothesizing on whether the variances are equal or one is less than or greater than the other, we can argue that the hypothesized ratio of the variances remains 1 for the 3 vases discussed here. We can hypothesize on any value for the ratio of the variances. In doing so, we need to simplify the ratio of population variances with the hypothesized value in the F statistic. As a result, the F statistic is simplified to the ratio of the sample variances or a scaled version of it. In order to conduct a hypothesis test on variances of 2 normal populations, we need to start by finding the value of our F statistic by plugging in the values of sample variances and the hypothesized ratio, and then compare this test value to the rejection region. If F0 falls in the rejection region, we will reject the bull hypothesis in favor of the alternative hypotheses. In the two-tailed test, the rejection region is from -infinity to f value of half alpha with n-1 and m-1 degrees of freedom, and from f value of 1 minus half alpha with n-1 and m-1 degrees of freedom to positive infinity. Please note that as F distribution is not symmetric, the rejection region is not symmetric as well. For the upper-tailed test, the rejection region is from f value of 1 minus alpha with n-1 and m-1 degrees of freedom to infinity, and the lower-tailed test has a rejection region of -infinity to f value of alpha with n-1 and m-1 degrees of freedom. Let's go over an example together. We want to study whether the height variation of 2 European countries are the same at alpha equals 1%. The first group consists of individuals of Italian nationality. The second group is taken from individuals of German nationality. Looking at the question, we can identify that we are interested in studying the variances of 2 different populations. The null hypothesis states these variances are equal, while the alternative hypotheses state these variances are not equal. Equivalently, we can say that under the null hypotheses, the ratio of the variances equals to 1, and under the alternative, the ratio of the variances does not equal to 1. To conduct this test, we need to load the f-test function and pass the sample of heights, the hypothesized ratio of variances, alpha, and alternative arguments. The function report the corresponding f0, p-value, rejection region, as well as a two-sided confidence interval around the ratio of population variances. In this example, as p-value is greater than alpha, we fail to reject the null hypotheses. An operating characteristic curve for the f-test is a graphical tool used to evaluate the probability of failing to reject the null hypothesis, type 2 error or beta, under different true variance ratios. The f-test is commonly used to compare two population variances by analyzing the ratio of their sample variances. The operating characteristic helps in determining how effectively the test can detect deviations from the null hypothesis when the true variance ratio is different from 1. To use an operating characteristic for the f-test, first, identify the significance level, alpha, and degrees of freedom for both sample variances. The x-axis represents the true variance ratio, while the y-axis shows the probability of failing to reject the null hypothesis, beta. Each curve corresponds to a different sample size, and larger samples result in steeper curves, meaning higher test power. If the beta value is high, the test has a low chance of detecting a real difference, indicating that a larger sample size may be needed. By analyzing the operating characteristic, we can adjust sample sizes or critical values to balance type 1 and type 2 errors effectively. Thank you for watching this video.
See you in the next one.